Good day everyone and welcome back. Today's session, our topic for discussion is regarding key single line diagram or main single line diagram. In this type of drawing, this type of single line diagram, you don't have to, the protection and metering will not be seen in this type of single line diagram because this is the overall overview of the entire power system. So it will be congested if those information are being drawn in key single line diagram. Okay, so right now this is the complete, as you have seen on your screen. This is the complete electrical power system for a certain oil and gas nuclear plant. Okay, so later we're going to make it zoom out to make it visible. Right now we have this the entire screen for the single line diagram to understand the interconnections of the entire system. Okay, so from here we have here a two transformer. Actually, the primary side of the transformer is 132 kV, okay, and is stepped down to 33 kV. Okay, our configuration right now, our scheme is a double radial system. That's why if you can see here, we have here two incomers. Okay, so every time, okay, most of the switchgear here are in dual configuration. Okay, so let's start from here. We have here a step down transformer from 132 kV to 33 kV. This one here, we have two 33 kV switchgear. Okay, this and this one. Okay, downstream, okay, we have here a distribution transformer that it steps down from 33 kV to 400 volts. So from here we have here a 3 LV switchboard, okay, or 3 LV switchgear. This two here, it's a double radial system, while this one here, the third one, is a single in radial connection. Okay, so let's discuss one by one the each system of our power system. So let me make this one more visible. Okay, so from here I will discuss only on the left side or on the right side because they are similar electrical equipment. Okay, so let's start on our upstream of our single line diagram. Okay, so here our transformer is, the voltage system is, the primary is 132 kV, the secondary is 33 kV. But as you see in the single line diagram, it is mentioned the secondary side of the transformer is 34.5 kV. Okay, normal practice, standard practice, the secondary side has to be more voltage, or has to be multiplied by 105% against the system voltage or the actual nominal voltage of the plant. Okay, so here, that's why we have here the secondary side of the transformer is 34.5 kV. Okay, our transformer vector group, our primary side is connected in star, while our secondary side this is it is connected in delta. Okay, it is YND1, meaning the LB lags high voltage 1 means because our the flow of is in for the vector group identification is counterclockwise. 1 means that is leads by 30 degrees. Okay, so that's the way we interpret it on this. Okay, so why we propose delta instead of the normal Y connection in the secondary side of the transformer. Okay, so let's bring this one down. Okay, here in one of our 33 kV switchgear, this is 33 kV. Okay, so in one of our 33 kV switchgear, we have this one and this one. These are water injection pump motors, and this water injection pump motors, it is rated 7,500 kilowatt with variable speed drives. So when we have this huge capacity of variable speed drive, okay, there will be undesirable harmonics in the power system. So it is being envisaged, okay, to mitigate the harmonics in the power system. It is being our transformer vector group has been decided to make it in Y in the 1, or the secondary side of the transformer is connected in delta connection. So that is one of the reason, because in delta connection, the third harmonic present in the phase magnetizing current of the three-phase transformer is not present in the line current. Okay, the third harmonic components are co-phase and hence cancel out in the line current. Okay, so the third harmonic components are flows rounds the closed loop of the delta. The delta connection only allows a sinusoidal flux and voltage with no third harmonic in the line. So those are one of the reasons why we make it the secondary side to be in delta connection. Okay, so after that we have done this. The rating of the transformer, both this transformer A and transformer B, is rated 48 on-an, and with fan it is rated 60 MVA. Okay, so on-off 48 and 60 MVA. Okay, so we have here our voltage percent impedance to be 12.5%. Okay, so what's this percent impedance? By the way, this is the percent voltage required, okay, to circulate rated current flow through transformer winding when another winding is short-circuited at the rated voltage tapped at rated frequency. So this percent impedance is related to short circuit capacity of the transformer during short circuit conditions. So that's why when we are going to prepare for a key single line diagram, this is one of the important information to be seen in the diagram. Okay, last we have here the tapping of the transformer. We have here plus minus 8 times the step is 1.25%. Okay, so this side I will not repeat the information from this side, okay, because the same information we have on this side. Okay, so we have done on the transformer, right? Let's go down. Okay, this is our cable connection. This is cable. Okay, both these are cable connections. Since our secondary side line is delta connected, that's why we provided this zigzag transformer from here. So why we have the zigzag transformer from here? Okay, the neutral formed by the zigzag connection is very stable. Therefore, this type of transformer lends itself very well to establishing a neutral for an ungrounded three-phase system. So our three-phase system here is ungrounded, so that's the reason why we provided a zigzag transformer. The zigzag connection in power systems trap triple harmonics. So what are those triple harmonics? 3rd, 9, and 15 currents. So the windings trap the harmonic currents and prevent them from traveling upstream, where they can produce undesirable effects. So okay, so we have here also on the both side of the incoming feeders, we have the zigzag transformer, and it's being connected so that we will have a grounded secondary side of our power our line. We connected here a neutral earthing resistor. It is rated 100 amperes. We call this one a high impedance neutral earthing resistor. Okay, so we go downstream. This is our incomer of 33 kV switchgear. This is rated 1600 ampere. Okay, so this is the symbol for our switch, earthing switch. Okay, so here, as you can see this, okay, these are the typical information you can see in a key single line diagram. Okay, so since we have two buses here, this is called bus A and this one bus B. The rest information are the same. So our system voltage is 33 kV in 3 phase, 3 wire, 50 Hz. Bus bar rating is 1600 ampere, 25 kilo ampere, 3 seconds, and this is GIS is a gas insulated switchgear. Okay, 3 seconds for the medium voltage side and 1 second for the low voltage side. So it is rated 3 seconds because on upstream, normally the release setting is higher than 1 second. Okay, so in order to coordinate the upstream relay going to downstream, normally on the, it could be here 1 second, but in this project, the proposed time rated is 3 seconds, 25 kiloamperes. Okay, that's why it's important to perform a short circuit analysis. Okay, normally in IEC standard short circuit analysis, there is a minimum short circuit and a maximum short circuit. So the maximum rating short circuit is being utilized to have an information on how much short circuit withstand capability to be proposed on a switchgear. In our case, for this 33 kV switchgear is 25 kiloamperes. Okay, so the same as on the bus B side. Okay, so let me, this one smaller. So okay, these are the outgoing feeders. Okay, so we can see from here, normally when you prepare you propose a switchgear, it's either medium voltage switchgear and low voltage switchgear, normally you have to provide a spare. So from here we have a spare feeder. It is a transformer feeder. It's fully equipped transformer feeder. Okay. And we have also here, it's a cable fully equipped spare feeder also. Okay. So the rest are being connected to its respective load or another 33 kV switchgear. Going down, okay, so this broken line here, this is the symbol of our power cable. Okay, here we have another two transformer from here. Okay, and these transformers are rated 2.5 MVA. This is AN because this type of transformer is a dry type transformer. Okay, so the vector group is then 11 and the percent impedance is 6%. On top of tapping point here is plus minus 2 by the steps is 2.5%. Okay, so this information from here and also here is the same since this is only redundant configuration. Okay, so here since the proximity of this transformer going to our LV switchgear is very close. Second, because the rating of our secondary side of the transformer is 4,000 ampere, it's very difficult to provide a cable here. That's why it's being proposed here. Okay, we have here these are the bus duct. Okay, so this symbol are bus ducts. Okay, so we have here an LV switchgear. Okay, so it's been stepped down from 33 kV to 420 volts. Okay, so but the power the system voltage for our secondary is 400 volts as what I have mentioned earlier. Okay, on sizing of the transformer side is being sized 105% against the actual system voltage of the transformer. Okay, so this is our bus A of our LV switchgear and this is for the bus B also. By the way, the incomer, we have two incomers and one bus coupler from here. These are interlocked to each other and these are with having high speed automatic change over. Okay, if there's any problem on one of the line, okay, this bus tie or bus coupler here will automatically close. There will be no interruption. Okay, to ensure that there will be a continuous supply of our loads. Okay, this applies to the rest of our double radial system medium voltage switchgear and the 400 volt switchgears. That's why we have also here, we have this incomer here. Okay, two incomers and a bus coupler here. So it's an automatic change over as well. Okay, so if you have 4,000 ampere, okay, rating of our secondary side of our transformer, the incomer also has to be 4,000, the same size, and with the bus coupler. Okay, so we have here bus A, 400 volts of 0.4 kV, 3 phase 3 wire plus neutral, 50 Hz. Rated of our bus is 4,000 ampere, 85 kiloamperes our short circuit withstand capability of this switchgear, and 1 is rated 1 second. Okay, the same information also what we have here. So from here, okay, so the same for the 400 volt switchgear, it's good practice to have also to provide spare from both side of the bus A and bus B. Okay, so and these are the outgoing feeders of our LV switchgear. Okay, so we have 3 LV switchgear here. Okay, let's go first on our another 33 kV switchgear from here. So this is our 33 kV switchgear, right? Okay, going to the right side, we have here a separate 33 kV switchgear for our water injection pump, which is rated 7,500 kilowatt. Okay, from here, from the case single line diagram, is not mentioned what's the exact rating of the transformer, because in the key single line diagram, okay, there is also a dedicated single diagram for each switchgear from here. So this switchgear, as you have seen, there will be another single line diagram that will mention undated all the information for our loads. Okay, this is our second. Okay, this is our second 33 kV switchgear that caters only on the water injection pump motors. Okay, this one and this one. Okay, so from here also we have 2 incomers. Okay, 2 incoming feeders. Okay, and 1 bus coupler. Okay, so we have also bus A here and bus B this side. So it's 33 kV, 3-phase, 3-wire, 50 Hz. It's rated 1,250 amperes. Our source circuit withstand capability is 25 kiloamperes for this switchgear, and also 3 seconds. Okay, so we have done the 3 33 kV switchgears. We have here the remaining 2 LV switchgear. Okay, so from here, there is an outgoing feeders that is both bus A and bus B, that is being also feeding this, we call this one emergency switchboard. Emergency switchboard meaning the other incoming power supply is taken from a diesel engine generator. In our case, this LV switchgear is being fed also by a 1000 kVE diesel engine generator. So the purpose of this emergency LV switchgear is to supply all the vital or essential loads. Okay, so if you see from here, okay, it's also a double radial system. Okay, our incomer here, we have here 2000 amperes, rated 2000 ampere, and also the concept is automatic changeover. Okay, so in this case, we don't have a bus coupler on our emergency LV switchgear. Okay, so just we mention only bus. Okay, rated 400 volts, 3-phase, 3-wire plus neutral. The frequency 50 Hz, 2000 ampere. Okay, and it's rated 65 kiloamperes in 1 second. So these are our outgoing feeders for our emergency diesel emergency LV switchgear. Okay, so what are those loads connected on this switchgear? We have here emergency air compressor. Okay, also the power supply for our UPS, our HVAC system also connected to the emergency LV switchgear. The auxiliary, this is the auxiliary supply for our medium voltage switchgear. Auxiliary supply also for our transformer. Okay, the auxiliary supply for our DC, our diesel generator package. Okay, and these are the essential loads. Okay, the vital loads, which the emergency lighting panel, the outdoor lighting panel, and the socket panel. Okay, so we have here this is also in radial system, but it's a single radial system that the power source is taken from this switchgear. Okay, so this is the third LV switchgear we have. it's on the incoming feeder is only single because this one are the non-essential loads, or we call it a normal loads only. What are those loads that are considered to be non-essential loads? If you can see from here, these are the multi-purpose panel, the normal lighting panel, the outdoor panel, and other loads that are being considered as normal loads. Okay, okay, so this is our complete, if you see, this is our complete key single line diagram. Okay, probably in our next video we will be preparing a detailed single line diagram each of these switchgear from here. Okay, meaning detailed single line diagram, we will be providing the information for the control and metering information on that particular drawing. So it means we will be providing the information regarding what are those relays required for each feeder, okay, and what are the metering required for each system or for each feeder. Okay, so thanks for watching. Please do not forget to like, share, and subscribe.